Hello, Assalamualaikum. In this video, we are going to see the function of Bernoulli equation in describing fluid in motion. Just to recap, in the video part 3, we have learned about useful of continuity equation to see the mass balance of fluid flow in a pipe. However, the continuity equation only explains the relationship mostly related to fluid velocity, flow rate, and cross-sectional area. How about the pressure difference in the pipe? If the pipe at point A is at higher level or position than at point B, will it affect the value of velocity and pressure at both points? In 1738, Daniel Bernoulli, in his book Hydrodynamica, introduced the concept of increase in the speed of a fluid occurs simultaneously with a decrease in static pressure. In his theory, he explained the Bernoulli equation is an approximate relation between pressure, velocity, and elevation, and it's valid in region of steady incompressible flow where net frictional forces are negligible. Look at this figure. This venturi meter has a manometer cylinder that attached to the large diameter pipe and at the smaller diameter pipe. The air flowing from the right to the left, and you can see in the manometer there is a fluid that contained in the cylinder where it shows different height in both cylinder that attached to the large diameter pipe and small diameter pipe. If you observe carefully, you will see the difference of the height between them. The difference height is due to the pressure difference inside large diameter pipe and the small diameter pipe. Another proper example of Bernoulli equation or Bernoulli concept If air flows through the tube, the manometer reaches a greater height in the narrow section. That is why the Bernoulli equation is an approximate relation between the pressure of the airflow in the cylinder, the velocity of the airflow, and the elevation of the pipe. The Bernoulli equation is also an approximate equation that is valid only in the inviscid region. I hope you still remember the difference between inviscid region and viscous region. Just to recap, inviscid region is the region or the location where the viscosity effect is considered negligible. Meanwhile, viscous region is the location of the flow where the viscosity effect is considered. In this figure, you see the airflow is flowing above the surface of the airfoil. Whenever the airflow passing over the surface of the airfoil, you will see two different colors of streamlines. The streamlines colored by pink velocity vector is considered Inviscid region, whereby the streamlines that colored by the gray velocity vector close to the wall is viscous region. As I mentioned earlier, Bernoulli equation is approximate equation that is valid only in the Inviscid region. So let's go a bit detail on how scientists derive Bernoulli equation. Bernoulli equation is essentially an equation that is obtained from the conservation of linear momentum, where it is commonly known as second Newton's law. What second Newton's law says? Second Newton's law says that the total force is always equal to the mass of the particle or the object times the acceleration. But for the fluid motion, the Bernoulli equation is the conservation of linear momentum for a fluid particle moving along a streamline. For example, if you look at this figure, this particle is moving along the S direction, and then there are few forces that involve along the way of the particle while moving at the S direction. Then the total force that involved is equal to the mass of the particle times the acceleration of the particle. While the particle moving, there are few forces involved. The first force is occur at the direction of the particle moving, where this force push the particle to move along the streamline. I hope you still remember that force is also equal to P times A, pressure times area. So in the first force involved while the particle moving is P times dA. dA represents the changes of the area of the particle while moving. Another force, which is force number 2 that involve, whenever the particle moving, there is another forces that in the opposite direction of the particle. It's involve the pressure plus the difference of the pressure or the pressure changing times dA. The third force that involved in the while the particle moving is the weight of the particle itself. After we know all the forces that involve while particle moving, we can get them all together in an equation that can be described from the force, the total force of the particle at the S direction equal to the mass of the particle times the acceleration of the particle at the S direction. So firstly, we take the force number 1 here, P times dA, and then second one we put the force number 2, P plus dP times dA, but remember it's in opposite direction, so it's minus. And another one is W, but the W itself is not according to the S direction.
So we have to a little bit derive the W. So this is W, and then this is the normal direction of the S direction. So this is S, and then this is theta. So W and S. We want to have force at the S direction. So simply put, sine theta is equal to S over W, since W is the hypotenuse. So you want to make S a subject, so W sine theta. So you put back the W sine theta in here, equal to M, which is the particle kilogram times velocity times dV over the S. This one becomes acceleration. So we still can simplify this equation. Firstly, we look at the M. M mass of the particle is also equal to rho times V. Careful, V here is not velocity, but it's actually volume of the particle. Rho is the density of the particle. So rho times volume equal to rho times dA times ds. dA ds, dA is the area, S is the length of the particle, so it's become volume. Another one is W. W, as we know, is the weight of the particle. It's actually equal to mass, which is kilogram, times gravity. You simply insert the derivation of m from this one into the m, then you can have rho dA ds times g. Another one is that we still can simplify is the sine theta. So you just put the sine theta like this. This is the x direction, this is the z direction, and then this is the s direction. So dd, all the d's represent the changing or the difference of particle, why the particle moving. Then the theta is here. So you can have sine theta is equal to dz over the hypotenuse, which is the s. And then having these three simplification, you put it back in the same box of equation, and then you will see that we can put all of them together, minus dpdA. Why minus dpdA? Because pdA minus dpdA, then you just cross out all of them, leaving us only minus dpdA. And then you replace w with rho g dA into this equation, and then you replace the sine theta here with this, and then you can have this one as well. Replace the m.
You place the m with this one, and then you maintain this one. From all the variables in this box of equation, we can simply cross out some of them and then put them in simple form. So we are now having only this one. We just cross out all the dA as well. Then we have only minus dp minus rho g dz equal to rho v dv. And then actually v dv, you still can simplify it into half of it, dv power of 2, having the derivation of dv. And then you put all of them again in the table, and then you can have dp over rho. You just bring down the rho plus half of dv power of 2 plus g dz. And then for steady flow, you can simply integrate the dp over d over rho, then it will become only p over rho plus v power of 2 over 2 plus gz. So Bernoulli equation says, as I mentioned before, steady incompressible flow, we can make use this Bernoulli equation specifically. And if you do have let's say a pipe, like the same pipe that I show you at the beginning of this video, you want to have flow properties at point 1, you want to know flow properties at point 2, you can simply, but before that you have to assume and you have to know that the flow in the pipe is steady flow and it's incompressible flow. Then you can simply use Bernoulli equation at point 1, Bernoulli equation at point 2. Then you simply put the equations in this relation. So Bernoulli equation at point 1, Bernoulli equation at point 2. Bernoulli equation also states that the forces acting on a fluid particle along a streamline is actually the summation of kinetic, potential and flow energies of a fluid particle is constant along a streamline during steady flow, when compressibility and frictional effects are negligible. Why we say that? Because the kinetic and potential energies of the fluid can be converted to flow energy or vice versa during the fluid flowing, causing the pressure to change. In the Bernoulli equation, we can identify that the first P here is the pressure that we want to measure. It is also known as static pressure. Second form of the equation is rho times v power of 2 divided by 2 is actually represents the dynamic pressure of the fluid. And last form here, you should be familiar with this because in the first chapter of our lesson we talk about fluid in statics. Are you still remember P equal to rho GH? So H here represents the Z, and G and rho exactly the same. And this form of equation is actually hydrostatic pressure. An example of the static, dynamic and hydrostatic pressure can be explained by
this very widely used flow measurement device, which is
named pitot tube. If you browsing in the internet and search for pitot tube, you will see varieties of pitot tube available in the market and mostly used on the aircraft, but the concept of pitot tube always similar. In the pitot tube, they should have at least two parts of the pressure holes. First pressure hole is the stagnation pressure hole at the tip of the tube. Second one is the static pressure holes, which is the two holes at the surface of the tube. After that, you look at this diagram. How can the pitot tube and the piezometer is useful to visualize the stagnation pressure, the static pressure, and also the dynamic pressure. For example, if you do have, let's say, air flow that flowing in this region colored by the pink color here, we can see that there is a stagnation point at the tip, like this one, stagnation point at the tip of the hole or the tube of the pitot tube, and then another one is the piezometer that have specific height of the fluid, and also in the pitot tube specific height. So we want to measure the velocity. As I mentioned, the velocity can be derived directly from this pitot tube in the previous slide. So from this we can specifically tell the pressure at this point is the stagnation pressure. That's read by the height of the fluid in the tube, in the pitot tube, and then the static pressure read by the height of the fluid in the piezometer. The difference between the static pressure and the proportional static pressure is this one, which is proportional to the dynamic pressure. So let's go a bit more detail. So limitation of Bernoulli equation is at least in 6 conditions. So Bernoulli equation is only valid for the steady flow, not applicable for unsteady flow. Second, only valid for frictionless flow. No shaft work should be included in the system. If the shaft work, for example, like involve pump, turbine fan, or any impeller, Bernoulli equation doesn't valid anymore. Bernoulli equation only valid for incompressible flow, where the incompressible flow, the density is always constant, and it's not applicable for compressible flow, where the density is not constant anymore. No heat transfer should be involved and only flow along a streamline. Okay, let's see a few examples. How can we use Bernoulli equations or a set of Bernoulli equations to measure fluid properties at specific locations? For example, look at this water discharge from large tank. Okay. Specifically, these questions want us to know what is the velocity at the outlets of the tap. So this is the large tank, water tank. This is the tap out, the water flowing out, and then they give us 2 locations. First one is point number 1 at the surface of the water in the tank. Point number 2 is at the cross-sectional area at the outlets. So they want us to calculate what is the velocity at point 2. So as usual, you put down the equations that related, P1 over rho g, V1 power of 2 over 2g plus Z1 equal to the set number 2, P2 over rho g plus V2 2g plus Z2. So for now, we have Bernoulli equation at point 1, Bernoulli equation at point 2. So mathematically, we can have few assumptions to simplify this set of equations. So firstly, we go form variables by variables. So we go first variable, which is the pressure. We look at pressure 1, we look at pressure 2. So pressure 1 at the location of the surface of the water. Location 1 and location 2. So location 1 and location 2, in this condition, they mention in the text, or specifically both of them open to atmosphere. So pressure at the surface of the water is actually equal to the atmosphere. Both of them atm, this one also atm.
No, what's it?
Definitely you can cross out both of them because it will give you zero value as well. How about the second variable, which is the velocity? Velocity at point 1, velocity at point 2. Velocity at point 2, definitely we know that it has to be any specific number or value because we want to calculate velocity of water that flowing out. However, velocity at point 1 is quite tricky. Velocity at point 1, what is the velocity of point 1? Velocity of point 1 is actually the water that decreasing over time. So whenever the water decreasing over time, it's actually very slow and almost 0 meter per second. Why we assume that? Because the size of the water tank is large relative to size of outlet hose. So the outlet hose is very small, but the water tank surface area is very big, so we almost cannot see that the water is decreasing. So we assume at steady flow velocity at point 1 almost 0. Okay, then we took out v1. How about z referred to the height of the position? So look at the point 1 and point 2. Point 1 referring to z1, point 2 referring to z2. Okay, to know what is the value of z1 and z2, we have to look at, usually in the figure they give us these symbols. Where is the reference point? So reference point noted by 0 in this figure is referring to 2. So basically z2 is the reference point, so z2 is equal to 0. Then we can take it out. However, z1 is equal to 5 meter, right? This is z1, so z1 is maintained. Okay, then we try to solve. We use whatever leftover variables in the equation. So we write it down, z1 equal to v power of 2 over 2g. Okay, then if you want to know the velocity, so the velocity 2, then mathematically solve it, quite simple, z1 times g square root, then we got the v2. Okay, that's the first example. How about the second example? Look at this boy playing with the water hose to make the water jet that coming out vertically to the air. So in this figure they show us point number 1 is when they zoom in, and then they show point number 1 is at the location before the obstruction by the finger. So this point 1. Point 2 is at the top of the water jet, where basically the water reach the maximum point and then it go down. Okay, let's do this together. How can we understand point 1 and point 2 using Bernoulli equation? So we write down point 1 over rho g plus. So how to solve this? They ask us maybe velocity at point 1, or maybe velocity at point 2, or maybe the height of the water jet. We don't know yet, but we can simply try to figure out from the simplification of the equations that we have here. So pressure at point 1 we don't know, pressure at point 2 open to the atmosphere, right? Because pressure is on the air, so it's actually pressure, atmospheric pressure. How about pressure at number 1, point 1? Do you think pressure at point 1 equal to atmospheric pressure? I don't think so. It must equal to any numbers or specific value pressure because it's inside the hose and before the obstruction. So P1 we maintain, okay, and P2 we maintain as well because they have different value. Okay, how about the second variable, which is velocity? velocity 1 and velocity 2. Look at velocity number 1. Velocity number 1 is before the instruction. Velocity number 1 is before the obstruction. So before the obstruction means the boy's finger obstruct the flow and almost close the hose, and the velocity before the finger is very slow and almost equal to 0 meter per second. So V1 is almost 0 meter per second. How about V2? V2 is at this point. What do you think? So velocity at this point must equal to 0 meter per second. So when it stop moving, that means 0 meter per second. So both of them are 0. So this one, V1 is 0, V2 is 0. And then how about Z1 and Z2? Z1 is the reference point. Yeah, so this one is 0. Then it's left to you with few variables here, P1 over rho G. Okay, so if you want to know the height of the water jet, is actually equal to the Z2, and then you calculate P2 and P1. Okay, the third example here is the siphoning out gasoline from a fuel tank. Let's take a look at this figure. So for example, let's consider this car mistakenly filled in with wrong gas fuel. So for example, this car should be filled with petrol but accidentally mistakenly filled in with diesel. So we need to bring out or take out the diesel from the car, and usually the mechanics use siphon tube that useful to flow out the diesel from the tank. So according to the figure here, the gas tank has the point number 1, which is at the surface of the gas in the tank. That's noted as point 1. At point 2 is at the outlet of the tube before the fuel flowing to the gas can. So basically it's point 2. And point number 3, so usually the gas siphon tube is quite long, and to make sure that the wrong gas flowing smoothly from point 1 to point 2, they hang up a bit higher than point 1 and point 2, and then it's noted here as point number 3. Okay, so how can we make use this figure to figure out specific fluid velocity at point 1, point 2 and point 3? So point 1, point 2, let's say in this equation in the gray box here, we consider the comparison of Bernoulli equation at point 1 and at point 2. Point 1 is at the surface of the gas tank, point 2 is at the outlet of the siphon tube hose. Okay, so we write down P1. Oh, they already finished this one. Let me do this again. P1 over rho G plus V1. And now we try to simplify the equation based on the assumption. So P1 and P2. P1 is at the surface of the gas tank. Gas is flowing out. And then at point 2, at the outlet hose, basically both of them ATM, atmospheric pressure. So we can cross out both of them. Okay, again, how do we know this is atmospheric pressure? Usually if it's not atmospheric pressure, it will tell in the question. Second, it will show us like a meter of pressure gauge. Okay, then second variable that we have to check is velocity. So velocity point 1 and velocity point 2. Velocity point 1, velocity point 2. Velocity point 2 must have specific value, right? Because you know that whenever at the outlet the flow of the gas running out, so must have specific value of velocity at point 2. However, at point 1, similar with the assumption of the large water tank in the previous example, so V1 also consider almost 0 meter per second because the size of the tank is large. The size of the tank is large. Siphon tube hose, siphon tube. Okay, so this one take out as well. V2 we do have it. How about Z1 and Z2? Okay, which one is the reference point? So look at the figure. They said that reference point is at Z2 with 0 meter. So Z2 equal to 0. Now we use the leftover equations to calculate Z1 equal to V2 power of 2 over 2G. Then if you want to know, let's say V2, you just push away the 2G, then Z1 times 2G square root.
How about at point 3? Let's say you want to know maybe the pressure at point 3. If you want to know pressure at point 3, you may use either point 1 or point 2. In this example, they use between point 2 and point 3. So you write down the equation, Bernoulli equation at point 2 and Bernoulli equation at point 3. You got P2 over rho G, V2, we got V2 over 2G and Z2. And then P3 at the top of the siphon tube position, P3, V3 and Z3. Okay, let's have a look. P2 equal to, again, ATM. How about P3? Is it also equal to atmospheric pressure? I don't think so, because pressure inside the tube that fill with the gas must have specific pressure value. So P3 we maintain. How about V2 and V3? V2 and V3 actually the same fluid that coming in. As we know that mass balance of at point 3 and at point 2, they, remember, m dot equal to A equal to rho times velocity times area. So m dot 3 equal to m dot 2. So we do have rho velocity 3 area 3 and rho velocity 2 area 2. We took out rho because density is constant of the gas. Area 3 and area 2, both of them are the same because it's siphon tube, and then at point 2 is still in the tube, right, at the outlet. So cross-sectional area at point 2 and cross-sectional area at point 3 are the same. So when both of them, you can take out definitely V3 equal to V2. So V2 take out, V3 take out. Then finally you can have the leftover equation that PATM, which is from the P2 over rho G equal to P3 over rho G plus Z3.
Okay, it's enough for now for this video, and I see you in the next video for the example of problem solution. I think that's all for now. Thank you very much. See you in the next video.